Hello everybody again. You are welcome to clip 2 in part 5. So we introduced CDMA system, direct sequence CDMA, and the last clip, clip 1, we came to this slide where it indicates actually that the transmitter and the receiver of some structure of with which indicates the multipath, as you can see here, of the signal. And also we assumed that we have n different transmitters, and this is only transmitter number I, and this is receiver number I. Okay, so this is the transmitter number I and the receiver for I transmitter. And we assumed here in this environment that we have maybe n different transmitters and in different receivers, and all of them, they use the same carrier frequency, but they use different codes. So we have ci and I. This is for the transmitter I, but for the others they use different codes, and those codes should be like low correlated. As we said, the best thing to be orthogonal, but even if they are orthogonal at the transmitter, however at the receiver, due to the different paths, different delays, we cannot maintain the orthogonality. So but we hope that they will have low correlation at the receiver side. Now we pick up the signal of this receiver I, and let us see mathematically how it will be. So this is the received signal Ri. So if we go, sorry, okay, so if we go to the uh, mathematical formulation, so this is the transmitted signal. So Si of t, transmitted signal from transmitter I, equal to square root of Bi of t. Bi is the transmission power of user I. Xi is the information signal. It is non-return to zero, so it is multiplication. Xi of t multiplied by Ci is the code, the spreading code of user I, and this is the modulation, cosine omega ct, because as I said, it is binary phase shift keying. Binary phase shift keying. This is what we assumed here. Of course, we can use also higher modulation levels like MRA, and in that case we will need to use in phase and the quadrature phase cosine and sine, but this is not the subject now here. And the expected value, or the average of xi times ci squared, we assume that equal to 2 to keep this pi of t as normalized power. Okay, and also we assumed here xi of t equal to the summation of bi of k hp of t minus ktb. Actually, this is the bit shape. So it can be, for example, you can assume that it is just rectangular for simplicity, of course, but of course rectangular usually we try to avoid because it has large bandwidth. We use some like some shaping like raised cosine or whatever. And also we have here the bit level, so it can be 1 or -1. Bi, I is from user I, and k is the number of the bit. For example, bi1 is the first bit from user I, bi2 is the second bit, bi3 is the third bit. Of course, we have maybe millions of them. And then we have here the code of user I, and it is exactly the same actually. Ci of k is C is for user I, and k is the number, is the level. Actually, it can be the first level, it can be 1 or -1 as it is, and hc is the chip shape, signal shape. It can be also rectangular. You can assume that it is rectangular, and you can see here we have tc is the time duration per chip, and here TB is the time duration per bit. So this is simply the mathematical formulation of the transmitter. This is the transmitter, sorry. So this is actually Si of t, okay? And now this is I transmitted in the wireless channel, okay, and how it is received. So the received signal will be Ri of tau and t, because we assumed that the channel, of course, is time varying, as we know. This is the reason that we put two times here, tau and t. And you can see that we this is the received signal. Okay, so the received signal, this is the for the channel gain between user I. You can see that k is from 1 up to n. Okay, n is the total number of transmitters. Okay, and remember here we assumed a single path per transmitter for simplicity. It doesn't mean that it is difficult if we consider the multipath. Simply, if you have multipath, you can add here only another summation where every transmitter, they have different paths. Actually, the other summation should be in here internally. So for every k, for example, user 1, we will have multiple paths. Maybe you can take 5 paths. Those are the significant paths. Okay. Then we have the square root of a jki. Again, I remind you that I assumed single path per user. Okay. Now then we have this is the channel gain between receiver I and transmitter K, and this is the power transmitted from transmitter K. You can see that we have some like different delay between each transmitter and the other transmitter. Every transmitter, it will arrive to user I with its own delay. This is tau K. Then xk is the transmitted data of user K. Okay, and ck is the spreading code for user K times cosine 2 by f0t, because all of them, they use the same carrier frequency, but the received signal will arrive with different phases. So every received signal will arrive with different phase because it has also different delay. And plus finally the additive white noise. Okay, so actually you can see here at the receiver I, they will use all signals from all k, or from all n transmitters. All of them, the signals will be received at the input of the uh, the receiver here. This is Ri, as you can see, and this is Ri of t. Okay. Yes. Now what I did here, I just separate the signal from the intended transmitter from the signal from the other interference, because we have n transmitters, but ith receiver wants to receive the signal only from the ith transmitter. So the others for ith receiver is just interference. I don't like to receive them. And in that case, just to keep or to bring this closer to your mind, or to your how this work. So assume that you have sensors, okay, transmitting sensors. Okay, so we have 10 sensors. They are sensing certain value from certain location, and each sensor, they should send the sensed value to certain receiver. Okay, so we have 10 transmitters and 10 receivers. All of them, they are sensing that physical value, and all of them, they are transmitting in the same time over the same frequency. Every sensor receiver, they want to receive the signal from its own transmitter, and I put in each pair between the transmitter and the receiver the same spreading code. So this is, maybe this makes it clear for you. Now that we have, this is the received signal, you can see that I just separated after the demodulation. You can see that the cosine now disappeared. Assume that we know in the receiver exactly the frequency. So and we can track also the changes in the frequency due to the Doppler effect of the channel. So now I can detect the original signal. This is my signal here, but the others are here. So the others are from k equal to 1 up to n, but k does not equal to I. It It means that all the other interference except the ith signal, they are in the second value here. The third one, or the second term, the third term is for the additive noise. Additive noise, I have nothing to do with it. It will be with me in every stage in my receiver. Okay. Now this is the received signal after the demodulation, but with before the production, or before the despreading of this with its own code. Okay. Uh, in the spreading or despreading process, we assumed, as I mentioned before, that they are almost orthogonal. If they are orthogonal, it means that Ci times Cj, this is the expected value, means that simply the integration in time, if we look to it in time. So this is the integration over one bit, one information bit, Ci times Cj. So if they are orthogonal and I does not equal to j, it means that they are different codes, then the result should be 0 if they are orthogonal. But again, because it is not orthogonal, they cannot be orthogonal due to the multipaths. Of course, we like to be orthogonal, but it will not be orthogonal. Then we put like square root of delta ij. I put square root because later when I take the compute the power, I take the square, then I will have delta. So delta ij is called the orthogonality factor. Orthogonality factor between different codes. And you can see that when I is equal to j, it means that when we take the autocorrelation of the same code, so the result is 1. So I will be very happy even if delta I is delta ij is not 0, but it to be like small, like for example 0.01 or less, I will be more than happy. Okay. However, that it can be sometimes even larger. It can be 0.1 or something like that. Okay. So this is the receiving part. This is Ri, the received Ri. Now I make the despreading process. I multiply with Ci, and then I take the averaging over 1 bit period. Here we assume that I take the first bit, but this is without loss of generality. So the same, it can be over any symbol or over any bit. Okay, here we take the simplest case that we assume that we have bit, but in general you can say that we have symbol. Okay, so now we have we take the integration from one symbol, so which means that before the integration, this is why d of t will be the received signal multiplied by the code I. So you can see that this is, we have code I, Ci multiplied Ci, but here we have Ck multiplied by Ci. We put here some other assumption, or another assumption, that we have delay like tracking. So Ci it has the same delay as the transmitting Ci. So this could be done over like delay locked loop. Okay, and finally, because we multiply everything by Ci, we multiply the noise by Ci, but this will not affect the noise, will be the same additive white noise. Okay, now what will happen after the integration? As you can see, after the integration, when we take the integration, so we have the integration of Ci times Ci, we have the integration of Ck times Ci, and this is equal to delta square root of delta ij, as we see before, and then this equal to 1. So the result will be square root of jii is the channel gain between transmitter I to receiver I times power bi, assuming that the power within 1 bit is fixed, bi. Also the channel gain, we assume that it is not changing within one time period, bt, because actually tb is very small time. For example, if our data rate is 1 megabit per second, it means that TB is 1 microsecond. So it is valid to assume that within 1 microsecond, the channel gain is the same. And also, this is the bit. B0, as I said, that we assume that this is the first transmitting bit for user I. Plus, now we have this, the interference part. The interference part is the all other transmitters from 1 up to n, but k does not equal to I. Okay, and then this is the contribution part of the interference. So it is multiplied by B0k, the other transmitting bit from all other users except user I, and this is the additive noise. This is finally the signal. If this part is very small, it means that the contribution over our original signal will be very small, and then the bit error rate can be very small as well. If the noise and interference is small enough, then we will have a very good bit error rate. If the noise plus interference together are very high, or it's very high value, then of course we will have lower or higher bit error rate, which means that we need to use more coding bits in order to correct the errors. Sorry. We can also define the signal to interference and noise ratio in this part. So this is the received signal of user I, the transmitting power, times the JII, divided by the interference part. This is the first part, is the interference from all other transmitters except user I, plus the additive noise power, average power. So this is called the signal to interference and noise ratio. And in order to compute EB over N0, as we saw before, that the probability of error is determined by EB over N0, not only by the signal to noise ratio. And we saw before that this could be achieved by multiplying this by the transmitted bit duration divided by 1 divided by the bandwidth of the channel. Actually, this was explained, I think it was in part 2. Okay, so which means that multiplied the signal to noise ratio, which means that it is FC divided by FB. FC is the chip rate, FB is the bit rate, multiplied by the signal to noise ratio. If FC divided by FB is called the processing gain or the spreading factor. It is called also a spreading factor. Okay, now if the bit error rate is high and I want to reduce the bit error rate, and it was because of the interference and because of noise, so we have the error in bits was very high, and I want to reduce them without increasing, for example, the power of the transmitter. Okay, what I can do, simply I can reduce the bit rate of the transmitter, so to increase the processing gain. Once I increase the processing gain, I will get higher EB over N0, which means that very good or excellent bit error rate. So the bit error rate will be very low, and of course after that also the packet error rate will be very low. Okay, how this could be utilized in like cellular network or in reality. Okay, in reality, for example, if you have transmitter and receiver, okay, and you have feedback channel, so they can tell you the packet error rate. If the channel gain is excellent and the interference is very small for that user, which means that you can utilize this condition by sending more data. How you send more data? Simply you increase FB. When you increase FB, of course the processing gain will be low, but still the SNR is very high already, which means that you can send very high data rate without like large error, probability of error. But if we have many users start to send in the same time, and now the interference becomes strong, or the channel gain becomes bad because the transmitter get away from the receiver, so the bit error rate becomes higher, packet error rate becomes higher. So how you can respond to this situation? Simply reduce your bit error or your bit rate. When you reduce bit rate, okay, if B becomes lower, then the processing gain becomes higher, and in that case the error also will be dropped, the error rate will be dropped. So you can, this is actually the main concept of the smooth capacity. So you can control the capacity easily by using the CDMA. Just by controlling this bit rate, you increase the bit rate, you reduce the bit rate, you can also manage the performance. And there's also another important part which is very critical in CDMA, that the power control, because you can see that the power of that of the of our transmitter will affect the EB over N0, but also the power of other transmitters. So in that case, we have to have like collaborative game in order that all transmitters they can share information and they can optimize their transmitting power in order to optimize the operation for every pair, for every transmitter and every receiver in that communication system. So this is the concept of here of CDMA. Actually, what we have seen here is called direct sequence CDMA. We have other types of CDMA systems, not only the direct sequence that the symbol that we have, symbol system that we have seen now, but we have also what is known as a frequency hopping CDMA, and we have also time hopping CDMA. Let us see them in fast way. A frequency hopping CDMA, simply it is based on that sense. We don't spread the original signal over wide or much wider bandwidth. So instead, we keep the same narrow band of the information signal, but every time we transmit in different over different carrier. Okay, so we can send it in this carrier. Assume that we have, let's say, 70 different carriers. Like this is actually, if I remember well, this is also the same used in Bluetooth. So we have carrier F0, we have carrier F1, F2, up to F69. So we have 70 different carrier. Okay. Every time I can select different carrier in order to transmit the information signal. Okay. So every time I select different carrier to send the transmitted signal. But how these carriers are selected according to this BN sequence. So I generate random numbers here from 0 to 69 based on some BN sequence. Okay, it is random for others, not random for me. So for the transmitter, they know on which frequency they will send, and they will inform it is receiver over the control channel that where it will be the second frequency where it will be, or if they use the same sequence, so it by default the receiver knows the second frequency where it will be. Okay, so in that sense, every time you can send over different carrier in random way for the others. So this can be the shape of the modulation. You can see that this is the modulator. This is the BN sequence generator. We have the frequency synthesizer here, and this will convert the result of this BN sequence into certain like carrier frequency. And now we have the modulator, and every time we use different frequency. What are the benefits of using frequency hopping CDMA? We have several benefits, like number one, it introduce some security. So if everyone that you jump from frequency to frequency in random way for the others, so it will be hard to track your data. The second thing, which is can be more important, is the possibility of having um, like multiple access without coordination. For example, I give example. This frequency hopping CDMA is used in Zigbee. Sorry, in the Bluetooth. Okay, now in the Bluetooth, maybe in the same room, you use your Bluetooth to send some image for your friend, and maybe some others they use the Bluetooth, for example, to connect their mobile to the internet. Some others use the same Bluetooth for some other things, like for example sending music or listening to their headphone by using the Bluetooth. All these Bluetooths are independent to each other, and all of them they use the same frequency. Why that they are not like make or have the collision between their transmitted packets, although that they all of them they send over the same carrier frequency. The reason is that because of the frequency hopping, so every transmitter sending over different frequency at at each time. So they switch from frequency to frequency. For the others are in random manner. So in that case, the probability that they will send on the same frequency will be small. Okay, so there is, it can be, for example, maybe 5% of the time the data are like we have collision maybe 5 times of the time, or 2% of the time, or 5%, or 10%. But in that case, if the collision is not hard, so the error correction, it might correct the errors, or the packets are received in error. But sometimes we don't even, if the data is not the data has the ability to mitigate with the errors, then like using the voice as we mentioned before, so that the receiver will just ignore that packet. But if the packet is very important, then the receiver will ask for retransmission. However, that even many Bluetooth receivers and transmitters can like cooperate, or cooperate actually in the same environment. Also Wi-Fi, many of Wi-Fi transmitters, they are sending on 2.4 giga frequency, this ISM band. However, that they can manage to have to work in the same frequency due to this frequency hopping in the Bluetooth. Okay. What is the third benefit? The third benefit is the frequency diversity. For example, if one certain band is within destructive fading, so there's outage, but when you switch every time from one frequency to another frequency, so you have the chance that you can move from destructive fading to constructive fading. So if you have deep fading in certain frequency, so you don't have to stay for longer time, because you will switch after some time to another frequency. And this concept is used in GSM actually. GSM mobile phone, they use also frequency hopping in order to have frequency diversity in the cells. So frequency hopping has some applications as well. Time hopping. The same concept of frequency hopping is used in time instead of frequency. So, for example, if we divide the time into this form, so we have time frames, as you can see, time frame 1, time frame 2, and within this time frame, we have time slots. We might have hundreds of time slots. And now, depending on the BN sequence result, so we select every time where we transmit our symbol, in which time slot. Can we set it like 2 here for example, in 7th, and here in 1st, and so on. Every time we select random time slot where to transmit our symbol, it is random for the others, but for our receiver, they know the sequence, so they can they know where it will be next time the transmission. Actually, this time hopping CDMA is applied in several systems, like or one of the main application here is called ultra wideband. An ultra wideband transmission, impulsive radio ultra wideband, where they use this impulsive radio. So we send impulse with very narrow time duration. It can be a couple of nanoseconds actually, and they can be transmitted over these time slots according to some like BN sequence, and also we over some coding technique. Some of these ultra wideband, they don't have modulator, so we transmit just impulse directly for very short range communication, as we will see them when we discuss about technologies later. So this is one form of the time hopping CDMA. So we have the impulse generator, we have the symbol shaping, where we have data here, and then we have programmable delay. As you can see, this is the programmable delay where we control it by the BN sequence. Then we have amplifier, and we have the transmitter. So of course we can have also modulation here. We have some kind called multi-carrier time hopping modulation, but it is not that widely used in practice. So because we have the OFDM, which solve most of the problems related to that. And then in the receiver, we have low noise amplifier, and then we have the correlator with the BN sequence, because BN sequence it will tell the receiver where the symbol was transmitted, in which time slot, and then we have the detection process. This is simply the time hopping CDMA. So after this slide, now we have seen most of the main concept actually of the CDMA. Of course, we didn't go in very details about with the BN sequence. This is called golden codes and the Hadamard codes, and how it is used. And actually, just we cover them and not very superficial way, but somehow we keep the concept clear for that. As I said, that we use some math in this part. Also, we will use some math when we talk about the OFDM, but we try actually to use the minimum math to have the concept clear. However, again, I repeat, if you face some problems in understanding when I talk about the mathematical part, so just ignore it. I hope that the general concept is clear about the main of the code division multiple access, either in direct sequence or frequency hopping or time hopping. Thank you very much and see you in the coming clip when we talk about the OFDM. Thanks a lot.